When you mix camphor with sodium borohydride and methanol, it turns into isoborneol. This video is about the mechanism for how that happens. Sodium borohydride is really a source of hydrogen nucleophiles. A nucleophile is a molecule that has a full negative charge, a partial negative charge, a lone pair, or a pi bond. If you have one of those, you have a nucleophile. If you don't have one of those, you don't have a nucleophile. With sodium borohydride, NaBH4, if you take that and draw it out, that molecule looks like this. So the boron is in the middle, surrounded by the 4 hydrogens. That whole group altogether has a negative charge. The negative charge on that is balanced out by the positive charge on the sodium. So how is this a source of hydrogen nucleophiles? Boron is a metal, and metals have very low electronegativity. That means that they give away their electrons. They give away their electrons and become slightly positive, and whatever they're bonded to gets those electrons and becomes slightly negative. In this case, that's the hydrogens. So each of these hydrogens is slightly negative. Each of these hydrogens is a nucleophile. Because they're slightly negative, they will want to stick to anything that is slightly positive. So when sodium borohydride knocks into camphor, the carbon that is double bonded to oxygen on camphor is slightly positive. It's bonded twice to the oxygen. Oxygen is really electronegative, so it pulls electrons to itself, becomes slightly negative. Whatever it's bonded to, in this case, this carbon, becomes slightly positive. So, that slightly positive carbon will attract these slightly negative hydrogens. Those hydrogens will take their electrons and attack that carbon. This carbon already has 4 bonds. If it's going to make a new bond, one of the bonds it has to break. That's going to be the weakest bond, one of the pi bonds. The pi bond breaks and the pi electrons go onto the most electronegative place nearby. That's the oxygen. If you're thinking in terms of the curved arrow patterns, this would be classified as a nucleophilic attack. In terms of storytelling, nucleophilic attacks add atoms onto a molecule, and in this case we're going to be adding hydrogen. So whatever the nucleophile is, that's what you add in a nucleophilic attack. So after this first step, you'll have essentially the same molecule, but the pi bond will be broken. These electrons that were in the pi bond will go just onto the oxygen, which now will have a full negative charge. And the carbon there will have this new hydrogen bonded onto it. That's the hydrogen that attacked. As the hydrogen attacks, it pushes this oxygen up. And so the oxygen faces the top of the molecule. The reaction isn't quite done because the oxygen has a full negative charge, and that isn't stable. To stabilize charges, the curved arrow pattern that you want to do is a proton transfer. Proton is just referring to an H+. Hydrogen, a hydrogen atom, is just a proton with an electron going around it. If the hydrogen loses the electron, so that it has a positive charge, it's just a proton. As you move an H+ around, you can change the charge on a molecule. Charge tells you how unstable or stable a molecule is. So when you change the charge, you change stability on a molecule. The source of H+'s that we're going to use to stabilize this negative charge will be methanol. And that's written as CH3OH in our reaction here. So what's really significant about methanol in this reaction is that it provides an H+. Oxygen here is very electronegative, so it pulls electrons to itself. Anything it's bonded to loses those electrons and becomes slightly positive. So this exposed hydrogen here is slightly positive. And when it bumps into the negative oxygen rips it off. The electrons that were holding on to it snap onto the most electronegative place nearby. That would be that oxygen. And you'd end up with the final product, isoborneol. So just to compare down here, notice these are the same. Remember that hydrogens aren't drawn in explicitly in skeletal structures, so that hydrogen is still there. It's just not written explicitly. And now this oxygen will have this hydrogen bonded onto it. So essentially, this reaction, reducing camphor to isoborneol using sodium borohydride and methanol, is 2 steps. The first is a nucleophilic attack by this nucleophilic hydrogen of sodium borohydride. When that attacks, the pi bond breaks, the electrons go onto the oxygen, which then gets a full negative charge. That's stabilized by the second step, a proton transfer from the methanol. And that's the mechanism for how camphor would be reduced to isoborneol using sodium borohydride and methanol.